ماذا لو أن الكفاءات الجزائرية من كافة أنحاء العالم تجتمع معاً؟ ماذا لو أن هذه الأدمغة بمختلف تخصصاتها تتكاثف لتطوير التعليم والبحث العلمي للنهوض بالجزائر في مختلف المجالات؟ هل تعتقد أن هذا مستحيل؟ أبداً، فالحلم يتحول إلى حقيقة من خلال الشبكة العالمية للعلماء الجزائريين إيناس. رغم أن إيناس هي مؤسسة غير ربحية وتعتمد فقط على تبرعات الأفراد، إلا أنها استطاعت أن تبني جسوراً من التعاون وتبادل الخبرات بين أبناء وطننا الحبيب من الداخل ومن مختلف بلدان العالم، ساعية لصقل المهارات واحتواء المواهب وتبادل الخبرات وإيصال التجارب النافعة لخدمة الوطن.
All right, good morning, good afternoon, ladies and gentlemen. Thank you for joining us in another webinar in the series Earthquake Hazard Mitigation. This is Mohammed Amrouche. I am the Geoscience Group Leader of INAS. Webinar in the webinar senior series, where we are trying to share what is being done in the field of earthquake hazard mitigation. Invitation. So in this presentation, Dr. Ehsan Jamali, I will first briefly introduce Dr. Ehsan. So Dr. Ehsan Jamali Hondori received his master degree in exploration seismology from the University of Tehran in Iran in 2009, and the PhD degree in geophysics from the Kyoto University. So in 2016, he was a research geophysicist at JAPEX, Geoscience Institute. Hello, can you hear me, Ehsan? Sorry.
Sorry, I didn't hear you, but now I can hear you.
Sorry, I think we had
your voice was kind of broken. So
sorry, I think we had a small technical problem, and now we're back. So I would like to apologize for our audience for this little problem. So this month we are very pleased and honored to have Dr. Ehsan Jamali Hondori. Good afternoon, Dr. Ehsan. Thank you very much for having us.
Thank you very much.
So let me just have a quick introduction of our guest keynote speaker today. Dr. Ehsan Jamali Hondori received his master degree in exploration seismology from the University of Tehran in Iran in 2009, and the PhD degree in geophysics from the Kyoto University in 2016. He was a research geophysicist at JAPEX from 2013 and from 2013 to 2019, and then joined Atmospheric and Ocean Research Institute, AORI, at the University of Tokyo as a postdoc research fellow. Since January 2022, he's working as a geoscience with Geoscience Enterprise Incorporated on geothermal resource exploration in Japan, and visits the University of Tokyo as a guest scientist. His research interests include seismic reflection tomography and full waveform inversion for velocity and building, reverse time migration, TIAN subduction, and zone depth imaging and fault stress analysis. And today he's going to share with us his very exciting research. It was just published in Nature Scientific Report, where he's going to discuss structural and physical properties of the plate boundary fault of the 2011 Great Tohoku earthquake. I hope I didn't miss anything, Dr. Ehsan.
Yeah, that's okay. Thank you very much for the introduction.
Please, you can go ahead. The floor is yours. Let me just share your slides. Please go ahead.
Thank you very much. Good afternoon, good morning, good evening, depending on where you're listening to this presentation. And I would like to start my presentation, which Dr. Mohammed just introduced. So for today's presentation, I will start with some brief introduction about the 2011 Tohoku earthquake, or the Great East Japan earthquake. And I will give some review of seismic reflection method and how we used this method for field data acquisition and processing, and how we built the geological model and did the seismic depth imaging to finally calculate the physical properties of the subducting sediments at the plate boundary fault. And after that, I will show some results and conclude my talk. I'm sure all of you have heard about the 2011 Tohoku earthquake, which was the most powerful earthquake ever recorded in Japan. And the tsunami that followed the earthquake was quite massive. It could reach the heights of like 40 meters in Miyako City in Iwate Prefecture. And unfortunately, the disaster left behind almost 20,000 people died and more than 6,000 injuries, and 2,500 people still missing. So this is the latest report in last year after the 10 years anniversary of this disaster. And the other disaster that happened following the tsunami was the nuclear accident in Fukushima Daiichi power plant. And you can see in the image here, in the pictures here, that how big this disaster was. And you can see, for example, this ship was moved to the ceiling of this building, or the tsunami waves that could pass through the protecting wall. So the big question here was that why this kind of big tsunami happened. Actually, nobody expected this much large tsunami to happen in this area. And if we look at the Japan Trench structure here, for example, we can see that the Pacific plate is subducting beneath the host plate with a rate of like 8.6 centimeters per year. And the hypocenter was quite deep, almost 30 kilometers. But previously, before 2011 earthquake, everybody was thinking that these kind of megathrust earthquakes will not generate or will not propagate the rupture to the shallow parts, and probably the rupture will be stopped in this zone here. But the truth is that after this earthquake happened, everyone noticed that the rupture zone of the 2011 earthquake was extended to the trench, and all the plate boundary fault was ruptured up to the trench. And this is the case that nobody expected. And because of the massive co-seismic slip and the movement of the huge amount of the water, actually the tsunami happened. So we were interested to study this area to know what actually caused this kind of big issue to happen, and what caused the rupture propagation up to the trench. So we focused on the co-seismic slip area in this contour map that you can see. This is actually the epicenter. And we used seismic data, which was acquired along line D13. And we tried to process the seismic data and do some depth imaging, and then calculate the physical properties of the underthrust sediments to see what's the effect of these physical properties on the fault stability. So some other researchers already well studied this area. For example, we can see this paper by Dr. Kodaira from Jamsted, who showed that the horizontal displacement near the trench was almost 69 meters. And another study, for example, by Dr. Suji, showed that there are so many different events observed at the seafloor, for example, at this location, site 2E, they observed that there is active seepage of the pore fluids through the fault system in this area. So later I will show more details about this, but these are just some review of the previous studies in this area, and we will refer to them later to compare our results. Another study which was published in Science in 2013 was by Ujie, who used the IODP drilling samples at the JFAS site. As we could see in this map, there was IODP Japan fast drilling project right after the earthquake to see what is the structure of the sediments in this area. And they could drill down to the plate boundary, like 800 meters below the seafloor. And at this location, actually, the water depth is like more than 7,000 meters. So they could reach to the plate boundary fault almost 820 meters below the seafloor. And they got the samples and brought to the lab. And this paper actually showed that their laboratory friction experiments showed that the very low shear stress is presented by the samples of this zone. And also the structure or the material of these sediments are mostly cementite-rich pelagic sediments, pelagic clay, and also very clear evidence of thermal pressurization effects was observed on the sediments from the samples. So that's why the shear stress was quite low on these IODP samples at the site. Another study by Fulton, also published in Science in 2013, used the temperature anomaly at the plate boundary fault, and they actually installed some temperature measurement observatory, and they recorded data for like more than a year, and then processed the data, and finally they could attribute the temperature anomaly to the dissipated frictional heat during the 2011 Tohoku earthquake. And they concluded that friction coefficient at plate boundary is almost 0.08, which is quite low, and shows why the shear stress is very small in this area. Another study in tectonophysics, 2013, showed that there are two groups of slow slip events which are migrating right before the 2011 earthquake towards this zone. And there is possibility that these slow slip events have connection with the triggering of the 2011 Tohoku earthquake. So for our study, actually, the objective is to calculate the physical properties of the underthrust sediments because these physical properties directly control the stress state and slip behavior of the plate boundary fault. And this is kind of unique because previously no one tried to calculate the physical properties along the plate boundary fault. As I said, in JFAS drilling program, they just selected one point and reached to the plate boundary at that point. But we know that there could be some local effects, or that could be quite difficult to expand the results from just one drilling point to the whole 2D or 3D area. So we try to use the 2D seismic data and calculate these kind of physical properties in a more covering zone, or we try to cover a larger area by these kind of 2D analysis. And how to achieve this goal? As I said, we just use the reflection seismic data, which is acquired by Jamstack. I will show later. And we use the empirical relationships between P-wave velocity and porosity, and then calculate pore fluid pressure, vertical effective stress, and shear stress. And we also calculate the fluid overpressure ratio to see the fluid drainage condition at the plate manifold. So because this presentation is not just for the geophysicists, I mean, this is probably watched by some people from different backgrounds. So I try to keep a little bit review of seismic reflection method. And I'm going to explain how we use the seismic waves to image the subsurface. In this slide, we can see 3 different models. And on the left side, we have a uniform model, which means that all the model has been made by only one material. And if you look at this top axis here, that's actually the horizontal axis, or the direction on the surface of the ground. And we have also the vertical axis as the depth. So we are actually looking at some cross-section of the Earth's model that we have for now as a uniform model. And V here refers to the velocity at which P-wave propagates in subsurface. So we have a source for seismic energy, and this source is excited, generates the seismic wave. Here we have used the acoustic approximation, and the seismic wave is propagated in all directions and reach the receivers at the surface that are shown by the green triangles. So in the other case, we have 2 layers, and in the middle panel, actually, the velocity in second layer is higher than velocity in the top layer. And in the last model, it's the opposite. The velocity in the lower layer is less than the velocity of the top layer. So we want to see what is the effect of this kind of configuration. We can see that when the seismic wave is propagated at the boundary, there is kind of reflection from the interface of the layers. And if we compare these two, we will see that there is a difference between the reflected energy from these 2 boundaries. So that says, if we look more closely, if the velocity is increasing in the second layer, this kind of pattern of the energy is very similar to the direct energy which is generated by the source. But if the velocity is decreasing, for example, here V2 is smaller than V1, this kind of pattern is kind of opposite. So for example, here you can see the white, strong white color here, but that's black here. So if we look at the recorded data after the simulation, if we select the data from the receivers at the surface and we display the signals like this, we can see that this opposite pattern is observed here. So that's what we call an opposite polarity or reverse polarity, because as we will see here, the physical properties of the layers control how the reflection is generated. Let me introduce this parameter, which we call reflection coefficient, for different layers, for different boundaries between layers here. For example, let's say this is kind of Earth model. We are looking at the cross-section of the Earth model, which has these kind of 5 layers. And each layer has some density and some velocity value for P-wave propagation. So we define the reflection coefficient at the boundary by this formula, which is actually the multiplication of the density and velocity. And we subtract the value from the second layer and from the top layer. So after calculating the reflection coefficient, we can see that if the velocity is increasing, this value will be, assuming a constant density, of course, here. If the velocity is increasing, the reflection coefficient will be positive. But if the velocity is decreasing, the reflection coefficient will be negative. And these reflection coefficients will make the reflectivity series, what we call here. And we have a seismic source which generates kind of seismic signature that we can see here, or seismic wavelet. So the combination of this seismic signature and this reflectivity series, which we do by convolution actually, generates the seismic trace or seismic data. So we can see that the reflectivity directly transfers to the seismic trace. So if we know this seismic trace after proper processing, we can actually find out if the materials have high velocity or low velocity or any other kind of property. But the truth is that in real case, the geology is much more complex, as you can see in this simulation. And also, we put the source and receivers quite close to the surface because we don't want to go too much deep. Actually, it's not really easy to, for example, go very deep for acquiring the data using the normal techniques. Of course, there are some techniques that we do that, but for the normal acquisition, we usually keep the source and receiver at the surface, close to the surface. So the data may look something like this, and that's quite complex, as you can see. Another point is that the model is actually in depth domain. You can see that the vertical axis is in depth. This is our geological model, or our real Earth model is in depth domain. But the data that we acquire is in time domain. You can see the vertical axis here is time domain. It means that we have to go back from the time domain by processing the data and build the geological model in the depth domain. And that's what we do in different steps of our data processing. So in specific case of marine seismic survey, we have another problem arising, which is the reflection from the surface of the sea. So that's the boundary between water and the air, and that's quite reflective because the density and the velocity of the environments are completely different. Actually, no seismic wave transfers to the air from the seawater. So that makes it a very strong reflecting boundary. And it generates what we call multiple reflections. You can see, for example, after this wave is propagating down and going up and again reflecting back. And this continues as long as you simulate or record the data. Doesn't matter. So what we need to do is to take care of these kind of complex phenomena when we acquire the data and process the data and interpret the data. So in reality, we use different kind of acquisition equipments. For example, this is very small seismic acquisition set or equipment. In this picture, we can see 2 air guns. So these are kind of capsules which can keep the pressured air and release the air at the desired or arranged time, and that energy will propagate downward, as we could see in the simulations, and generate the seismic reflections. So these are 2 air guns. And also we have the streamer cable here, which has the seismic sensors inside the cable. We call them hydrophones. And those seismic sensors can receive the data, can receive the seismic vibrations and record the data using the recording system that we have on board in the vessel. And usually this cable is handled by winch, and winch is powered by some power supply. And we have the recording unit inside the laboratory of the vessel. And depending on the configuration, this cable may have different lengths. In this case, this is 1800 long cable, but we may have much longer or sometimes shorter cables depending on the usage purpose. So these are some of the vessels that you can see with different size and different capabilities. Most of them were used for 2D seismic surveys, because these are like small scale vessels. But for example, this one is the 3D seismic vessel, which can acquire the data from different streamers simultaneously. So that's a different topic and different technique to talk about the 3D seismic survey. But for now, we just want to show that there are different kind of vessels that are being used in the marine seismic survey. So for the field data acquisition in Japan Trench, right after the earthquake in 2011, JAMSTEC, which stands for Japan Agency for Marine Earth Science and Technology, they used the research vessel Kyra in May 2011 and acquired 2D seismic data with this kind of configuration. So they used shot intervals of 50 meters and shot depths of 10 meters and receiver intervals of 12.5 meters inside the cable, as I said. And the receiver depth was actually very deep, 21 meters, quite deep in marine seismic, normal marine seismic surveys, because they wanted to stay away from the floating objects which came to the ocean by tsunami. So they just towed the cable very deep. And the number of channels was 444 channels, and the maximum length or maximum offset of the cable was almost 5,800 meters, and they recorded the data for 18 seconds. So we got the data from JAMSTEC, and we designed this data processing flow to process the seismic data and build the geological velocity model and do the depth imaging. And we will see that each step has some positive effect on the quality of the data, improving the quality of the data, and creating the final result. And I will briefly just show the result. I'm not going to go to the details of these kind of different steps, but we will have a chance to look at samples of the data, how the processing improves and gets the final result that we want. For example, this is kind of stacked section from the raw data. We just applied geometry and we did the stacking. For those of you who are geophysicists, probably this is quite familiar. You know how to do the stacking, but we used only the water velocity to generate this stack section. And you can see that in this initial or brute stack, there are like, it's not even brute stack, it's a very first step stacking just using the raw data. You can see there are bubbles, there is multiple reflection here, and everything inside this stack you can see. So step by step, we try to improve this by first applying the debubble, and then trying to apply the deghosting. And after deghosting, we try to remove the reflections from the sea surface, which are the surface-related multiples. We apply surface-related multiple elimination, SRME, to remove the multiples. And we can see that it's kind of working, but there's still some part remaining, and we will deal with that later. So just to make some QC that everything worked well, we can see the spectrum of the raw data before debubbling. And after debubbling, actually, these kind of knots in the very low frequency part are removed, which are related to the bubbles. And these are the ghost knots. And after deghosting, we can see that the knots are filled and the spectrum becomes more flatter. And we can see that this is, as I said, the stack with water velocity after the tsunami, but still some part of the multiples are remaining. So we apply parabolic radiant transform, PRT, and remove the remaining multiples. And after that, we do the velocity analysis to get the right reflections with the right velocity. You can see that the reflections recover after we do the velocity analysis. And this is the stack section of the whole line. You can see the incoming sediments on the Pacific plate part, and you can see the forearc in the western side. And we do the time migration to just create time migrated section. So this is the process which was done in the time domain, but we need to do, as I said, depth modeling. So we try to use the layer stripping technique to build our initial velocity model using this flow. So we get the water velocity at first, and then build the model in the depth domain. And iteratively, we try to add layers from top to bottom. That's kind of layer-based strategy. And we do the PSDM, pre-stack depth migration, in each loop and try to improve the velocity model. And once we are happy with this result, we do the tomography, grid-based tomography, to build the final model. And then we apply pre-stack depth migration. So this is the final PSDM section that we got. And you can see that this is the Pacific plate being subducted. Actually, we can see very nice reflection from the Moho here. And we have the, just let me overlay the velocity and the interpretations. You can see the Cretaceous unconformity here. And we can see the arc Moho here. And that's probably quite easy to understand how two plates are being imaged by the seismic data. So the color here shows the seismic P-wave velocity model, or P-wave velocity value. And you can see that there is a low velocity zone here, and that's our area of interest. That's our target area. We want to know what's happening here. So we select this area, and we continue with further calculations in this area, as I will show you. So before that, I want to show you how tomography improves the image of the seismic depth section. This is what we call, on the right side, what we call common image gather, and this is the PSDM section. So this is before applying the tomography, and after applying the tomography, you can see that the reflection becomes more flatter and more stronger in terms of amplitudes. So we can say that tomography is actually working quite well, even down to like 12 kilometers of depth here. You can see this is 12 kilometers deep reflector. So once we are happy with the velocity model, we can do more advanced imaging, which is reverse time migration, or RTM, because RTM has the ability to image the deeping reflectors much more accurately, and it has more benefits compared to PSDM. So we can compare, for example, these two. I'm not sure if you can see in this small size image, but if you have time, you can check the full paper to see the large size figures. So RTM can image, for example, this area better than this, because we can see the fault here much more clear. And also here, the seafloor is imaged better. And we have two zones here that I will show kind of zoomed panels in the next slide. Before that, let's look at the velocity values here. You can see that in the wedge-shaped low velocity zone, the velocity is quite lower than the upper plate, or even from the lower incoming Pacific plate we can see. So this is the area that we believe is quite important for our study. So let's see how we can interpret, or how we can understand what's happening here. So sorry, before that, let me introduce these boundaries here. So this is the backstop interface, which is the boundary between deformed sediments in this wedge zone and the undeformed sediments in the upper plate. And also we have the plate boundary fault or decollement here, which is shown by pink color. And we have the top of the oceanic crust with black color here. So you can see there is kind of horst and graben structure here. These horst and grabens are generated when the plate bending happens much far into the ocean, when the normal faults happen due to plate bending. And once those normal faults happen, this kind of horst and graben pattern is generated. And once the incoming sediments and the oceanic plate comes to the subduction zone, they just go beneath the upper plate. And let's look at this reflection from the seafloor. We can see that reflection from the seafloor has this kind of polarity, as I mentioned during the synthetic simulations, numerical simulations. We can refer to these polarities to examine what is the source of this kind of reflection. So this is the reflection from the seafloor. And seafloor has normal polarity because the velocity of the sediments is higher than velocity of the water. So it's showing the positive reflectivity and generates the positive or normal polarity. So we show the seafloor polarity with the green arrow, or the positive reflectivity or positive polarity with the green arrow. And we show the negative or reverse polarity with the blue arrow. And if we look at the reflections, for example, from the backstop interface, we can see that this is quite visible, that it's opposite to the seafloor polarity. That's why we can say that this is lower velocity below the higher velocity zone. And also we can see these two grabens here. At graben B, we can see that this kind of opposite polarity happens. So we expect that inside this graben, there is considerable amount of pore fluid, which is trapped inside the sediments. So we call them bucket sediments. Bucket sediments, which actually we refer to, include a lot of pore fluids within the pore spaces. On the other hand, in graben A, there is no strong reflection from the decollement. So we can say that probably this area has been already drained out. As we will see later, the reflection from the decollement is quite weak. So it means that not so much strong reflection we can see from top of this graben. And this is the same for graben C. So there are bucket sediments trapped inside this graben, and they have probably a huge amount of pore fluids trapped inside. And they make the opposite polarity of this reflection here. So this is the opposite polarity, and this is the normal polarity. This is reflection from the top of the oceanic crust, but this is the reflection from top of the bucket sediments. So after this kind of interpretation, it's time to calculate the physical properties. We already have the P-wave velocity, so we can calculate the porosity by using this kind of empirical relationship between P-wave velocity and porosity. And actually, we checked that this relationship matches very well with the samples that were acquired in Japan Trench, so we can rely on this empirical relationship. After calculating porosity, we can calculate bulk density and also void ratio. Once we got the void ratio, we can make a consolidation curve by fitting some linear line in the logarithmic scale between the hydrostatic effective stress and the void ratio. And we actually make sure that this line is fitted bestly and in the best way on the densely located samples from our data, so we can see that it goes very well within the high number of data points. So we make sure that the fit is the best one. And after that, we can calculate the effective stress. And if we subtract these two, we will get the fluid pressure, pore fluid pressure, and we can calculate the overpressure ratio. And on the other hand, we can calculate effective stress ratio, which we will see later. So for the results of these physical properties calculation, we can see that on the left side, we have the calculations for the plate boundary fault or décollement. And on the right side, we have the calculations for the backstop interface, which is the major fault between the deformed and undeformed sediments in the accretionary wedge and the upper plate. So we can see that the pore pressure is much higher than hydrostatic level, actually 82% to 60% higher than hydrostatic pressure for both the décollement and the backstop within 40 to 22 kilometers distance from the trench axis, which means in this area here. But for the backstop, actually, it drops down quickly, as we can see at this point, and reaches to the hydrostatic level. But for the décollement, it stays still higher than hydrostatic level, up to 2 kilometers distance from the trench axis. So we also calculated the uncertainty of these calculations. I'm not going to explain the details about the uncertainty analysis, but we can say that the maximum uncertainty near the trench is 17%, and at the 40 kilometers distance from the trench, it's almost 22%. So still, we can see, still with these kind of uncertainties, the values are much bigger than what we expected. So this is the pore fluid pressure, and this is the hydrostatic pressure, and we see that's much higher still, even considering the 22% of error. Also, we calculated the stress values, vertical effective stress and shear stress, and we compared our results with the JFAST drilling site C0019, and we noticed that the values are very close. So you can see at this point, the JFAST site is located almost 7 kilometers away from the trench. And we can see that our calculations match very well with these observations from the drilling points. So we use the same value as Fulton et al. For the friction coefficient to calculate this shear stress. And we will see that even if we calculate the friction coefficient from another method, it will be still valid. It will be in the same range. So for the fluid drainage conditions, we can say that we can calculate the overpressure ratio, or lambda star, which is the difference between pore fluid and hydrostatic pressure, and lithostatic and hydrostatic pressure, and the division of these two differences. We can see that two zones are kind of visible in this graph. So lower overpressure ratio means that fluids are already drained out, or there is a drainage system which can help the fluids to circulate to the seafloor. And we can see that in zone 1, this is actually lower, so it shows that there is possibility that fluids can easily or easier go to the shallower zones. And in zone 2, actually, this value remains almost constant, and we can say that fluids are kind of trapped here. So if we look at the seismic section, we can see that there are some faults inside the accretionary wedge, and these are the thrust faults which reach to the décollement in Graben A. So this is the zone 1 that can easily help the fluids to reach to the seafloor. But in zone in zone 2, above graben B, these faults do not touch the plate boundary fault. So the sediments which are located here probably have trapped fluids, and the pressure of the trapped fluid is quite high. We also calculated another quantity which we call the effective stress ratio, which is the division between the calculated effective stress and the expected effective stress under the normal consolidation conditions. So if the effective stress ratio is higher, it means that the fault is stronger and the coupling is actually better. But if effective stress ratio is lower, it means that fault is weakly coupled and it's easy to slip. So we calculated the same value for different subduction zones, for example, in southern Ecuador, in Nankai Trough, and of course in Japan Trench. And we confirmed that this kind of pattern or this kind of low effective stress ratio matches with the zone that was suggested by Ito et al. 2015 for the source of tremor and slow slip events in the Japan Trench. So we see the correlation between these two zones from 0 to 40 kilometers distance for both calculations. And we believe that the effective stress ratio is low in this zone. So that's probably another reason that the fault could easily rupture to the surface. And we used another method, which is the critical taper theory, and we calculated the static coefficient of friction or static coefficient of basal friction, UB prime, and we got the value 0.09 for the plate boundary fault using this method. And we compared the value with the dynamic value, which is observed from the JFAST site by Fulton et al. And we can see that these are very close, very similar. So there could be two reasons for this similarity. The first one is that because the geology of the subducting sediments is mainly clay rich, I mean, the clay content is quite considerable in the subducting sediments. So it has a very big effect on reducing the friction coefficient of the plate boundary fault. And also the data that we used was acquired only 2 months after the earthquake. So it means that probably the plate boundary didn't have enough time yet to heal. And it will take much longer time to restore the frictional state of the plate boundary fault. So in conclusion, I can say that we noticed that the pore fluid pressure is quite high at the plate boundary fault, and that's probably the main reason that the friction coefficient is very low, and fault rupture could easily propagate to the trench during the 2011 earthquake. And also we noticed that the back subinterface has a good drainage system, and also the fault geometry is different. So it's not possible, or it's not actually reasonable that backstop experienced kind of big slip during the earthquake. And we noticed two zones, as I explained, in Japan Trench, and zone 1 is well drained, and pore fluids could easily expel out from the plate boundary fault. So it makes it a little bit stable, but still lower than what we expected for the whole plate boundary fault. And zone 2 is quite showing quite low overpressure ratio, which means that shows very high pore fluid pressure and overpressure ratio, which means that it's quite unstable, and still we need to study more sites, probably using more data in the same area to see how we can expand this interpretation in maybe 3D or in different areas. I would like to thank Paradigm Emerson for providing the software for processing the seismic data. And also I would like to thank Jamstack for giving us the data for this research. And if you are interested, you can read the paper in full, and it's open access. You can easily access without any restriction from the Scientific Reports website. And thank you very much for your attention, and please feel free to let me know if you have any questions. Thank you.
Thank you. Thank you very much for the very interesting presentation, Dr. Ehsan. And congratulations again for the wonderful job and the publication in Scientific Report. It is indeed a really exciting work, especially that it falls within my specialty, geophysics, earthquake engineering, and you combine them. So really, congratulations for the fantastic job and for the presentation. So I would like to remind our audience that you can ask your questions in the comment section. Dr. Ehsan just finished the presentation, and he did a very good presentation covering the literature review of seismic reflection methods, and how he even explained and break down how they to break down the data, Jamstack data acquisition and processing, and finally shared the detailed map of the area and for the pore fluid estimation. So I will pick a few questions from our audience. I can see some questions here. One from Facebook. Thank you very much for the interesting presentation. What kind of simulation have you used in your review seismic reflection method? Seems you have an excellent boundary conditions and no reflection artifacts. So maybe a little bit some words about the simulation code you used in your experiments.
Thank you very much. Actually, this is just a simple finite difference modeling, and I applied perfectly matching layer PML boundary conditions on the sides, and also on top we have the free surface boundary condition for the marine case, or PML boundary condition again on the top for the uniform model and the 2 layers model or Marmousi model. So that's a finite difference modeling code that I developed during my PhD.
Excellent. So it is FDM simulation. Thank you very much. I'll pick another question from the audience again. The same person is asking, have you mapped any methane hydrate at the ocean bottom in the area? Probably, yeah. Japan is known to have some methane hydrate accumulations along the borders. So have you bumped into any methane hydrate accumulations?
Yeah, actually in Japan Trench, we didn't notice, or at least we didn't aim to find any methane hydrates, but we have actually a lot of seismic images in Nankai Trough, for example, or especially I myself was involved in methane hydrate exploration in Sea of Japan. So in other areas, yeah, we observed and we used actually very specific techniques for methane hydrate exploration, especially in Sea of Japan, in the Western Japan. But in this area, we didn't aim to, and also we didn't observe anything. So there could be, but we didn't actually aim to observe that. Or we didn't,
is it possible to map them with such large-scale seismic sections? Are they observable?
There could be resolution issues, but in fact, in Nankai Trough, we can easily see the BSR, bottom simulating reflector, for the gas hydrates, even using the same system. I mean, the Kyre, the vessel Kyre acquired the data from the Nankai Trough, and we could see BSR in those seismic images. But the difference is that the water depths in actually Nankai Trough is quite shallower than this Japan Trench area. At least for the area with gas hydrates, it's shallower.
Thank you. Thank you very much for your detailed response. So I personally have a few questions that I gathered along the presentation, if you don't mind. So
sure.
My first question is, have you considered using any IODP data? I don't know if you heard about the International Ocean Drilling Program with GQ from Jamstack. And did they try to drill around the area to get some core samples?
Actually, we are using that data, as I showed. Let me go back to the slide. So this JFast, let me change the pointer. Can you see JFast site?
Yes.
This is the IODP site that was
Okay.
drilled right after the earthquake, and we are using the samples from here to validate let me go to sorry, it's a little bit slow, but yeah. So first, you can see the samples shown here for JFAST. So we use these samples to make sure that velocity to porosity transformation is valid in this area, because we want to use this curve. Actually, this curve was built from non-kite trough data, but after we confirm that this fits to our samples from Japan Trench, we make sure that we can use this relationship in our study. And also the other papers that I referred to, for example, Fulton et al. Or Uji et al., they all use the data from JFAST, and we compare our results. Yeah, as I mentioned here. Yeah, this one. So JFAST site is actually the IODP site that you mentioned. So they calculated the effective stress using the temperature anomaly that they observed at the plate boundary fault. And we calculated the effective stress using this method, and we confirmed that these values are kind of matching. They are in close range.
Excellent. So yeah, thank you very much. Because I didn't saw the word IODP. I'm not very familiar with JFAST, and I understand that it was IODP data. Thank you very much, Ehsan.
Yeah.
So before concluding, I have one final question. Actually, we were just discussing before starting the live about the data availability in Jamstack, and you told me that they provided the data.
Sure.
Openly. So yeah, we can remind our audience that you can probably also apply for this kind of data if you're interested to look at it. Also, I was really surprised about the high resolution and very good quality of the data. It's really impressive and really very good, especially after doing the depth migration. So I would like to know, if did Jamstack provided pre-stack data or post-stack data migration? What kind of, I mean, did you use, can you do the processing yourself, or you just use the post?
Yeah, actually we did the processing. For PSDM, we used the Paradigm software, and for RTM, actually I used my own code that I developed. So for reverse time migration, I used my own code. And we got the shot gathers from the Jamstack. So it's raw data, it's nothing, just raw data without any geometry, without any processing. We got the raw data and did the processing all by ourselves. And as I said, we tried PSDM and RTM. So RTM is much more reliable for imaging the steeply deeping reflectors. So that's why we applied RTM on the target area. And that's what we did. Yeah.
Okay, thank you very much for your response, Dr. Ehsan. And with that said, I would like to thank our audience for attending, and thank Dr. Ehsan for presenting his work. We would like to remind our audience that we are still holding monthly webinars on the project Earthquake Hazard Mitigation. Probably for the next month in October, we are going to have 2 keynote speakers instead of 1, where they are going to try to cover a little bit the social seismology in Algeria. So please stay tuned in our International Network of Algerian Scientists page, and looking forward to see you next month. So again, thank you very much, Dr. Ehsan, for your presentation. And
thank you very much.
Thanks.
Thank you very much.